Morning. Right, at the end, there's a tutorial set of questions for next week and some more practice questions for Friday. We'll go through on Friday, all being well. Good week, everyone? No. Okay, so last time we were doing the Goldfinger mechanism for a lilac bromination, and we're now going to go through that. It's one of the most unusual mechanisms in rhododendron. So this is the Goldfinger mechanism. And as I say, it's a very selective way of halogenating a lilac or benzylic CH bonds. So what we start off with is N-bromosuccinimide. Which is that species there, cyclic imide with an NBr bond. And we have a trace of HBr, which is always present in this reagent. And we're heating it away. And these two undergo an ionic reaction to give us a small amount of Br2. That is why the reaction goes brown. So this gives us Br2, a trace of it, and succinimide. I'll leave you to have a go at working out that mechanism, but the side product in this reaction is the NH version of our imide. We're heating away at high temperature. Bromine's got a fairly weak bond in it. So under these thermal conditions, our trace of bromine may undergo homolysis to give us 2 Br dot. It's a chain reaction, so this is absolutely vital. We only have a trace amount of Br dot. So it's gone brown, and we've got some Br dots. Br dots then collides with our substrate, in this case cyclohexene. And the weakest bond in cyclohexene is the allylic CH bond. Weakest bond. And that bond strength is roughly 360 kJ per mole. So I don't need to learn these, just for showing you how important bond strengths are. Br dot, reactive, abstracts the hydrogen from our cyclohexene to give us a lilac radical. Which of course is in resonance with a degenerate resonance form in this case, and we generate HBr. And again, that's a good reaction because HBr's bond strength is 368, so we're going downhill. The beauty about this is now, of course, we've generated some more HBr. And HBr can now go back into the cycle above to give us some more Br2. So the product from H abstraction is a means of generating bromine continually throughout the reaction, so it stays brown. And then the final step is abstraction from our bromine molecule, like our lilac radical, to give us a CBr bond, specifically the lilac position, plus Br dot, which then of course is our chain carrier. and that goes back. So there are two intertwined chains. There's the continual generation of bromine, and there's the continuous abstraction and formation of the allylic bromide. Once the reaction is finished, we no longer generate HBr, and the bromine stops being formed, and it goes colourless. Hopefully, if the reaction has worked. So that's the Goldfinger mechanism. If I was to say shaken, not stirred, would that remind ourselves of the origin of this? Of course, it's a James Bond reaction. Okay, so that's the Goldfinger mechanism of allylic formation. And we generate a trace quantity of bromine, steady state quantity of bromine at all times. We don't want lots of bromine, as the bromine will add to the alkene in an electrophilic fashion. We need a low concentration of bromine at all times. It's essential. Okay, so that's the Goldfinger mechanism. We're now going to move on to perhaps one of the most useful reactions of all in traditional radical reactions, and that's what we call intramolecular functionalization. Intramolecular functionalization. This is developed by a chap called Sir Derek Barton, and it's a very elegant way of functionalizing specific CH bonds. So, the reaction occurs for a 6-membered transition state, and it's a consequence of what we call proximity of reacting centres, and it results in the functionalisation of the delta carbon of a chain. So we've got a radical species at one end, 1, 2, 3, 4, 5, alpha, beta, gamma, delta. From a species of that sort, we can functionalise specifically that carbon. So again, it's an example of where we've got reactive species, radicals are reactive, but we can actually use them to do very selective reactions. Okay, so this is the general scheme of what we call remote functionalisation, or intramolecular functionalisation. There's our radical at the end of the chain, and we're going to functionalise specifically the delta carbon. So alpha, beta, gamma, delta. We're going to introduce a functional group at that delta carbon which is otherwise inaccessible. So there's the CH bond at the delta carbon. 6-membered transition states are always good in organic chemistry, they're particularly stable. So that radical will abstract selectively the hydrogen atom from the delta carbon because it's occurring via a 6-membered transition state. And that occurs, of course, only if the XH bond strength is stronger than CH. That's the key thing. We're abstracting from the delta carbon because it's a 6-membered ring. That's fast. We're only going to see one example of this, but that radical can now react either with another radical species or with something like YZ, another entity, to introduce functionality at the delta carbon. And that could also be all Y dots. We'll see that in a second. That is remote functionalisation. We've introduced functionalisation at the delta carbon specifically, unlike free radical halogenation, for example, which can go all over the place. Right, so the so-called Barton remote functionalisation involves something called nitrite esters. and that's a nitrite ester, ONO. So if we look at any heteroatom containing molecules, we've got two heteroatoms next to each other. That bond in between them is usually quite weak. The ON bond of a nitrite ester is weak. It's a weak bond, about 230 kJ per mole. When I say weak, we're comparing to a CH bond, which is around 400. So that's a weak bond. We shine a light on it, thermalise it, focalise it. That bond will break. Give us two radical species. Now, if you look at the scheme above, we're doing an intramolecular reaction. Intramolecular reactions are really fast compared to intermolecular reactions. And that's why this particular reaction is a radical-radical reaction. It's not a chain reaction. So fast that these two species don't diffuse away. They remain in what's called the solvent cage. So the abstraction is very, very fast. So if you do a few bond rotations, we can draw our alkoxy radical appropriately with its delta hydrogen. Our NO dot.
Move up a bit, we can't see that.
Put it that on, sorry. I'm not good at high-tech things. Right. Organic chemist. So, there we go. Delta carbon with a CH bond. OH bonds are very strong. 464 kilojoules per mole. CH bonds are weaker. This abstraction will take place extremely rapidly. 600 transition states, going downhill in energy. And it happens so rapidly, we're still stuck in the solvent cage. Those two radicals haven't diffused away. So in this particular case, we have a radical-radical recombination to form a CN bond. That is what we call a nitroso compound. So we've introduced a nitroso group at the delta carbon very selectively. And we generated a nice strong OH bond. So that's around 460 kJ per mole. And the CH bond is approximately 410 kJ per mole. So that abstraction is a good abstraction, both in terms of 600 ring and in terms of bond strengths. Right, nitroso compounds. Ooh. Probably that's good on my set things. There we go. Right, so we've got a nitroso compound. Any of you know what nitroso compounds prefer to be in equilibrium with? What are aldehydes in equilibrium with?
Is it an oxide?
Oxime, brilliant. It's a tautomerism. Oximes are in equilibrium with their nitroso tautomer. Third tautomer is oxime. We lose a proton from that carbon and replace it on the oxygen of the nitroso compound. So we generate an oxime. An oxime is a very useful functional group. You can do all sorts of things with it. Nitroso compounds are toxic. They cause cancer, so oxenes are good. Right, so that's our final product. Functionalisation of the delta carbon. Right, beautiful reaction. There is a slight difficulty in as much as, if you look at what goes on here, we have to rotate certain bonds to get to our preferred arrangement for abstraction. So there is a loss in entropy in order to achieve that arrangement, because we've got to freeze out bonds to allow the abstraction to take place. And that is actually why this reaction has become extremely important in rigid systems where we don't have problems with loss of entropy. Right, so if you can just go to your back page and sort of split it in half. We're going to look at a group of molecules called steroids. Now, I'm a big fan of 3D. So I just want to remind ourselves a little bit about 3D representations of structures. Cyclohexane. Cyclohexane, we draw like that. Is it flat? What is it? Yeah, why is it not flat? My tutorial group know this. It's not aromatic, good. What's wrong with a flat cyclohexane? What's the internal bond angle of cyclohexane if it's flat? Maths, GCSE. 120. That's too big, we want 109. So the main reason that cyclohexane isn't flat is because it needs to get away from an extended bond angle. So it exists in a chair conformation. And I want to remind you how to draw chairs correctly. Do not draw them like that. That is not a chair. You wouldn't believe how many chairs I see in exams that look like that. Please don't. If you can take note of what I'm doing, this is a good way of drawing a chair. You draw two parallel lines for the left and right bond. You then head just off the diagonal and you come back parallel to that line. You then join the final two up. That is the correct representation of a chair conformation, where we have that bond parallel to that one parallel to that one, that one parallel to that one. It does look somewhat different to the wiggle on the right. At each carbon we have what's called axial and equatorial substituents. And people often get these mixed up. But every carbon is a tetrahedron. So if you just focus on that single point as being a tetrahedral centre, top right, there are only two possible locations for the other two bonds. There and there. That's a tetrahedral centre. And what you'll see is that bond is again parallel to the one that's two away from it. Which one's the axial one? Up one or the sideways one? Up one. Axials always alternate. So the next axial is there, next equatorial is there, and again that is parallel to the one that's three away from it. I'm not going to draw them all on. The one that people often get a bit mixed up is this central one. The axial one, of course, is vertical again. The equatorial one has to be parallel to one that's two away from it, which is there, not in the other direction. You wouldn't believe how many people draw it going in the opposite direction over that way. That is the correct representation of a cyclohexane chair. Now, this is very important in terms of steroid chemistry because they have lots of chairs in them. Right, here's a steroid. Classic steroid skeleton. 3 6s, 1 5 mid-ring. And they are rigid, they are beautifully rigid. There's no flex in those structures at all. So, if we do the Barton remote functionalisation with this compound, the first step will be homolysis of iron nitrite ester. We're going to functionalise ultimately one specific bond on that molecule to make an oxime. I'm now going to draw out that steroid in 3 dimensions. That is my left hand ring. That's the one next to it. And it's just repetition of what I've just done. Keep everything parallel. So that's what we call the AB ring system. We then go to the C ring, and then I'm pulling off the end. The 500 ring isn't defined. 500 rings are very flexible. That is a 3-dimensional picture of a steroid A, B, C, D ring. On this particular one, that's my O acetyl. There's my hydrogen. There's the CH3. And there's my oxy radical that I've just generated. So this is the beauty of the steroid ring system. Because that oxy radical has now only got 1 hydrogen it could possibly abstract that's 6 atoms away from it, and that's on that methyl group. Alpha, beta, gamma, delta. There's no loss in entropy, those things are stuck where they are. Not like the previous system where we've got bonds rotating, these bonds are stuck in a diaxial arrangement. So in this case, the abstraction of hydrogen from that carbon is incredibly fast. They can hardly avoid each other. So it's important you can get to draw a steroid in 3D to show which bonds are close to each other. I'm going to go back to 2D. So we've generated our OH bond. Driven by thermodynamics, I've generated a radical on that axial methyl. And again, I'm not going to draw the whole thing in. That's the rest of the steroid. NO dot is still in our solvent cage, even more so in this case, because that abstraction is so fast. We rejoin the 2 radicals to make our nitroso compound. OH. Blah, blah, blah. And as I say, the final process is always tautomerism, and O, to get the more stable oxime. So Derek Barton did loads of this, and all sorts of steroid systems. It's a very nice way of introducing functionality at what otherwise are almost impossible centres to functionalise. Beautiful reaction. Okay, so we've transferred our functionality from our oxygen to an otherwise unreactive methyl group. Right, so that's the Barton remote functionalisation of the delta carbon, and it's basically an aldehyde equivalent. So that's the Barton reaction. Non-chain, because we have this rapid intramolecular abstraction. NO dot doesn't diffuse away, and we ultimately generate a nice strong OH bond and a nice strong oxime CN double bond. And I'll leave you with one to have a look at. This is the formation of andosterone acetate. So if we do the same thing with this molecule, H nu, and we then hydrolyze our product, our oxime with acid, to generate a rather useful compound which has an aldehyde functional group in it. And it is in fact that carbon that we functionalise as our aldehyde. And hopefully you'll have a go at drawing that out and see why it might be that carbon we functionalise and nowhere else. Like practicing your 3D pictures. Okay. So I think that's one of the most elegant applications of traditional radical chemistry. You could not do that sort of reaction any other way, and you get a very useful functional group at the end of it on positions that you would otherwise be unable to access. So that's all the classic radical reactions. We've done Goldfinger, we've done remote functionalisation, we've done Markovnikov, anti-Markovnikov, halogenation. Perhaps the most important current application of radical reactions is their addition to alkenes. And that's what we're going to do in the last handout. My hope is to get through this handout this time and early next lecture, and then we'll go through some of the questions, particularly the latest ones there. Help with revision. So radical reactions to alkenes. This is modern synthetic radical chemistry, rather than these traditional reactions we've been looking at. So it's perhaps the most useful reaction for the formation of carbon-carbon bonds. So it's a very useful reaction for the formation of carbon-carbon bonds. Carbon-carbon bonds are one of the hardest bonds to form for an organic synthetic chemist, certainly in any selective fashion, and involves the addition of a radical to an alkene, which generates a new radical, and we get a chain. So these are chain reactions. So the classic way of generating radicals for this sort of system is to use AIBN, which, as I said last time, you do need to know the structure of AIBN. Very important. So this is AIBN. Know that structure. That's our initiator. We only ever use a trace of that species, and if we heat it or if we photolyze it, it decomposes. And it decomposes to give 3 entities: nitrogen gas and 2 tertiary radicals stabilised by resonance. The driving force for that, of course, being and good, yes, diminishing nitrogen. Rather a strong bond as well, then, the two. So it's both thermodynamic and delta H and delta S. That's good here. Remember, only a trace. We've got at least an equivalent of a trialkyl tin hydride in there. Tributyl tin hydride, common one. And we have a trace of tertiary radical. The tin hydrogen bond is relatively weak compared to a CH bond. We saw that last time. Abstract a hydrogen in our tin hydride, generates a stronger CH bond and a trace of the tin radical. All going downhill so far in terms of energetics. Those are the initiation steps, we saw those last time. The propagation steps are where it all becomes a little bit difficult because there's various competing processes that can take place. So we've got our trace of tin radical, and we've got an alkyl halide of some sort, usually a bromide or an iodide, the weak bond. So our trace of tin radical. Tin halogen bonds are relatively strong compared with carbon halogen bonds. We saw that again last time. So we abstract a halogen from our alkyl halide to give us our alkyl radical plus our tin halide, trace of alkyl radical. We don't want it dimerizing, we want to keep it low concentration. Our dot can then react with our alkene. There's our alkene with a group on it. We found out before that we generally generate the more stable radical when we add alkenes. So we attack less substituted ends and generate the more substituted radicals. And that's our initial product radical. And the final step, all being well, is that initial product radical will now abstract a hydrogen from tin hydride to give us our desired product. That is the desired sequence with 3 rate constants, K1, K2 and K3. Looks great if only those reactions take place and nothing else takes place. But there are of course a few difficulties here because radicals are reactive.
Excuse me.
What? Hello? Yep.
I've got copies of that handout by chance.
Of this one? Yep. Right. It could go horribly wrong. So, that process, we've got our trace of R dot adding to our alkene. So that's our desired process. So our desired process in step 2.
No one's got it though.
Take the whole lot down. Everyone got a handout? Yeah? Right. That's our desired process which we want to make sure takes place. With rate constant K2. But we could of course have a competing process where that radical whips a hydrogen away from tin. And that's what we don't want. So we don't want, if we're doing addition to an alkene, our initial radical to abstract a hydrogen. So if K2 is not large enough, then we get what we call reductive dehalogenation. We'll ultimately start with an alkyl halide, and we'll replace the X with an H. So reductive dehalogenation is unwanted. So we need K2 to be fast. The other problem we might face is that our initial product radical, which is this one, may not abstract hydrogen from our tin hydride. So we want it to abstract our H. And so that's our desired process. Unless you're working in the polymer section, what you don't want to happen is that radical to add to another molecule of alkene. Because if that could happen, we of course could have that happening over and over again to make oligomers or even polymers. So if K3 is not large enough, then we'll make a glue or plastic or something. So, when you're doing radical reactions, we need to control what happens as best we can in terms of trying to affect the rates of the individual steps. This is where the art of radical reactions comes into place. So R dot, what we generate first, must be more reactive than our initial product radical. With that towards the alkene. If it isn't, then we'll get polymers. We also need that initial product radical to be more reactive than R dot towards tin hydride, so that we don't reduce R dot, but we add our hydrogen to our initial product radical. And this is usually controlled by using alkyl radicals, which I mentioned in lecture 1 are what we call nucleophilic. And we react them with electron deficient alkenes, where my Z is an electron withdrawing group. So that makes the K2 very big. Nucleophilic radical adding to an electron deficient alkene, K2 is big. We also keep the concentration of that tin hydride at low at all times to prevent it reacting with R dot. And we do that often by gradual addition during the reaction. So there are some important things to think about when we're designing reactions where we add a radical to an alkene. I've got a couple of examples. We'll do the first one and I'll leave the other one for you to have a go at. So this is an example from a phosphodiamine synthesis. And I showed you this one in the first lecture. Well, we've got, if this sort of thing comes into an exam, the first thing you do is you look for weak bonds. What's the weakest bond in our system?
Carbon iodine bond.
Carbon iodine bond, brilliant. Particularly weak. About 214 mole. So when you get this sort of question in an exam, you write the whole thing out. You don't just assume that you get tin radicals. So I'm going to give you a model example of an answer to this sort of question. So you draw out your AIBM. And that's a trace. AIBN undergoes spontaneous decomposition at 80 odd degrees C. Give you N2 and our two radical species, entropy. tin hydride, weak tin H bonds compared to CH bonds. So we can abstract a hydrogen atom from our tin H bond to give us a trace of tin radical. And our stronger CH bond, and that's all the initiation steps. So we've got trace amounts. And I keep on harking on, but it is important. This idea of trace amounts of radicals at any one time is highly important, else we get unwanted dimerizations, etc. Quite rightly, the carbon-iodine bond is the weakest one. Tin-iodine bond is substantially stronger. Thermodynamically favourable abstraction from iodine gives me a carbon-centred radical. It's an alkyl radical. It's nuclear filled. We learnt that in lecture 1. It's an alkyl radical. It wants to react with an electron deficient alkene. So the rate of reaction with an electron deficient alkene will be fast. The alkene we've got in our system is electron deficient. It's a conjugated ester. Addition to that ester will be fast in a Michael fashion, conjugate fashion. And that will involve the formation of this carbon-carbon bond. That's the bond we're forming. So we generate a radical adjacent to the ester, stabilised by resonance. I'll come back to why it's formed on the top face in a second. And then the final propagating step is abstraction of hydrogen from tin hydride to give us our product. Extraction of H from tin hydride, and we generate our product. And our chain carrying radical, which then carries chain. So that's our cycle of propagating steps. Essentially replace our carbon-iodine bond with a stronger carbon-carbon bond. Right, I've got a quick point. So if you're going to get full marks on this question in an exam, I would also want you to tell me why that new bond is formed on the top face of the molecule, not on the bottom. We meant in lecture 2 what the geometry of alkyl radicals is, and they're rapidly inverting. So the radical centre that we've drawn here could be on the top surface or on the bottom surface of the molecule. This is where a bit of 3D comprehension comes into place, because our molecule has a specific 3D arrangement. What's called a bicyclo 3-3-0 ring system. So it's a bit like a cave. 2 founded rings making a cave, and a hydrogen bond, the CH bonds are pointing upwards. So our radical centre, which is there, can be either on the convex top or the concave surface. Much more accessible on the convex surface. Concave surface is sterically hindered. So this is this geometry of the radical that will react with our alkene. Much more accessible. So that is why we get addition to the top surface. We attack the convex, not the concave surface. This is convex. That's concave. Everyone see what I've drawn with it? Right, I want to very quickly shoot through a question we met last time, or 2 times ago, sorry, which is one of the practice questions I gave you. Which is all about the electrolysis of what we call 4-nitrovaleric acid. So we're told that electrolysis of that species in the presence of KOH, which gives a product B in excellent yield. Now you should be able to work out this straight away. First of all, if I take a carboxylic acid with KOH, what will be the first thing that takes place? Deprotonation. We've got an acid and we've got a base. First thing that will take place is we'll make potassium salt. Negative. If we then electrolyse this at the anode, the charge of the anode is positive. Minus an electron gives us a carboxy radical. Carboxy radicals are unstable towards loss of a nice gas, CO2. Which gives us a nice reactive prime radical. We're at the anode, so therefore we generate a high concentration of that radical at the anode. It can then dimerize in this particular case because we generate a high local concentration. And our product is the dimer. If you look at the data I gave you in the question, I gave you the molecular weight, I gave you CH, N and O composition, and this of course is an example of the Kolbe electrolysis. Okay, so next Friday, we'll finish off more with additions of radicals to alkenes, but particularly in cyclisation reactions, and then we'll spend some time going over the questions I've left you over there, those practice and revision. See you on Friday at 9.